We've all known that if you put water into a saucepan or a beaker or something, over time it will evaporate away. It will keep going, and the gas, H2O gas particles will leave, whilst the liquid particles will be in the container and they're going to be ready to leave. This is called an open system. An open system allows some of the particles to have the potential to be able to escape. However, oh, and by the way, eventually this container will be completely empty. If, however, we put this container under a bell jar, this would be called a closed system. Now, a closed system does not allow the products, especially the gas products, to escape. It keeps them trapped in the same system. So now they're all together, and what happens is there'll be evaporation. This would perhaps have started with a liquid level about over there. It will drop to a certain point, and at that point it will look like nothing happens any longer. There will be no macroscopic change. That means that you can't see a change, but there is microscopic change. And actually it doesn't mean you can see it under a microscope, because you can't see it under a microscope. You can't see atoms under a microscope. But at some tiny little level, you would be able to, there would be evaporation happening, and at the exact same rate as the evaporation is happening, some of these particles in the atmosphere around us, in the closed system, would be dropping back into the solution. In other words, they would be precipitating out. So evaporation and precipitation would be happening at exactly the same rate. That is an equilibrium situation, equal rate of evaporation and condensation. Firstly, for any dynamic, the word dynamic means changing. There's changing all the time on a microscopic level. Some liquid particles are becoming gas particles, some gas particles are becoming liquid particles, and vice versa. But it is happening at the same rate. In other words, as fast as it's going forwards is as fast as it's going backwards. In order to set up a changing balance, and that's a nice word I like for dynamic equilibrium, a changing balance, then I need firstly a closed system, and secondly a reversible reaction. In other words, it must be able to go backwards and forwards. So let's take a look at something a little bit more complicated than water evaporating. Chemical equilibrium is when the rate, it is defined as when the rate of the forward reaction is equal to the rate of the reverse reaction. Then you get a state of dynamic equilibrium. The changes will continue on a microscopic level, but there will be no visible or no macroscopic changes. The forward reaction would be, as an example, arbitrary A plus B gives me C plus D. The reverse reaction is going in the opposite direction. You look at my arrow, C plus D is turning into A plus B. So we have a reversible reaction. If I look at the reaction rate, let's take this example as an example, or this reaction as an example. This is my forward reaction. Hydrogen plus iodine gives me hydrogen iodide, but simultaneously hydrogen iodized can decompose into hydrogen and iodine. So what I can do is write it as one equation with a backwards-forwards arrow. In other words, we call this an equilibrium arrow. That equilibrium arrow goes backwards and forwards, and let's think about what's on the axes here. I've got reaction rate on the y-axis and time. So this reaction rate is initially fast. The forward reaction always goes fast first, and then slows down because I've got less and less of these things around as the reaction proceeds. The reverse reaction, there is no reverse reaction. Until I've made some HI, I can't start decomposing HI. So I first need to make some HI before I can start decomposing some HI. So the reverse reaction always starts at 0 because the rate of that reaction will slowly speed up, get faster and faster and faster. At the point, remember our definition on the last slide, where the forward reaction rate is equal to the reverse reaction rate, both of them have exactly the same value, that is your point of equilibrium. In the questions that will follow, you need to be very careful about what is on the axes. If we're talking about rate, we will interpret the graphs differently to if we are talking about concentration of reactants and products in solution. So watch very, very carefully. If it's rate, for equilibrium to have been established, the rate of the forward needs to be equal to the rate of the reverse. They're going to ask questions where they say, which reaction is represented by the blue line or the solid line or whatever? And it will always be, the one that started high would always be the forward reaction. The one that started low, in other words, which reaction is represented by the dotted line? And that would be the reverse reaction. So let's recap some of our terminology. A dynamic equilibrium are reactions that take place in both the forward and reverse directions simultaneously, and they are reversible reactions. We see macroscopic changes, we don't see any more changes in macroscopic situation, whilst the microscopic changes continue as the reactants change into products and the products change back into reactants at the same rate. So you can't see anything happening, but there is something happening on a tiny, tiny level. Just reminding us of some definitions. Our open system is when my products can escape, and my closed system is when the products and the reactants are sealed together. Factors that influence equilibrium. Now, things that can make this equilibrium, the forward reaction go faster or the reverse reaction go faster, an equilibrium may be disturbed. So once the balance has been established, if I heat it all up, I would get more water evaporating into my little bell jar, for example, and there would be a change. If I put more pressure on the system, that would cause a change. If I added more stuff to the system, that would be a change. So an equilibrium might be disturbed by changing one or more of the following factors. Those factors are temperature, concentration. You can't change the concentration of a solid. You can only change the concentration of a gas or a solution. Pressure, you can only change the the pressure on a gas. You can't change the pressure on a solid or a liquid. And then a catalyst is not actually a factor that changes the equilibrium, but I want to talk about it here because what happens with catalysts is that they speed up both the forward and the reverse reactions equally. There is a man, Mr. Le Chatelier, or I don't know, Professor Le Chatelier, but anyway, his name was Le Chatelier, and some people will pronounce that Le Chatelier, some people will pronounce it Le Chatelier, so there are lots of different ways of pronouncing it, and I'm sure there's only one way he pronounced it, but we all say it differently, and then he said the following: when an external stress, for example, a change in pressure, change in temperature, or change in concentration, is applied to a system in chemical equilibrium, so it already needs to be balanced, then I make a change, the equilibrium point will change. In other words, the state of equilibrium will change in such a way as to counteract or work against that stress. And we'll talk about that a little bit more in the next video.